Hyperbolic functions have a relationship with a unit hyperbola that is similar to the relationship that trigonometric functions have with the unit circle. The unit circle, you'll recall, has equation x squared plus y squared equals 1, and is of course a circle of radius 1. Associated with any point on the unit circle, we can give it coordinates x, y, but also if we identify an angle made with the positive x-axis, we call the angle t in this case here. The point has coordinates cosine of t, sine of t. And so here we would say x is equal to the cosine. I won't say equals because I'm not going to make it an equation. X colon. And y is represented by the sine function. Now here we have a unit hyperbola on the left, and it has an equation x squared minus y squared is equal to 1. That minus is what's making it a hyperbola. And just as the unit circle has a diameter of 2 because it has a radius of 1, the fundamental rectangle for the unit hyperbola is a 2 by 2 rectangle where the distance between the origin and the point of intersection between an edge of the fundamental rectangle and an axis is equal to 1. So it's 2 by 2 because it goes one unit out, 1 unit up and down and left from the origin. Now associated with a real number t, so now we're just going to say t is a real number. We're not going to call it an angle. On the unit hyperbola, there exists an ordered pair, let's say xy, and for any particular number t, that point has coordinates the hyperbolic cosine of t, hyperbolic sine of t. So for a point on the unit hyperbola, x is associated with the hyperbolic cosine, and y is associated with the hyperbolic sine. They are spelled COSH, or they're abbreviated COSH and SINH. And please don't try to pronounce it. It's not cosh. It's the hyperbolic cosine. Let's be careful with our language. Now, turning our attention back to the unit circle. Associated with that angle t is a sector. And you may recall that in general, the area of a sector of a circle is 1/2 r squared theta. Well, here r is equal to 1 because it's the unit circle, and theta is equal to t. So the area of this particular sector for the unit circle would be 1/2 t. Looking at the unit hyperbola, if we consider a segment that joins the origin to the point on the unit hyperbola, and just the area that's formed between that segment, that branch of the hyperbola, and the x-axis, then we have a region, the area of which is equal to 1/2 t. That t is the input variable for the hyperbolic cosine and hyperbolic sine at that point. Sometimes the question comes up, well, you're saying that the area of this sector is a equals 1/2 t, and the area of this triangular kind of not triangular thing is area equals 1/2 t. So question, are the t's the same? The answer is no. To show you why I'm able to say that, here I've included a unit circle within the fundamental rectangle of the unit hyperbola. And we know that that is the unit circle because it's got a radius of 1. Okay, I was a little off over here, but you can see what I'm talking about. My point here is the pink sector that we were just looking at would correspond to this portion of the unit circle, whereas this green shaded area is clearly bigger. And so it can't possibly be that the area of this sector is the same as the area of the green shaded area. And so the t's are not the same. T is not an angle, t is just a real number. It is the argument of the hyperbolic cosine and the hyperbolic sine for a point on the unit hyperbola. We aren't really going to be looking at this a equals 1/2 t relationship, but I just wanted to make sure that you knew that point about it. I also want to make sure you know that that was a way of understanding the hyperbolic functions, but there's actually a definition that doesn't involve the hyperbola directly. It is that the hyperbolic sine of x is equal to e to the x minus e to the negative x divided by 2. And you say, well, where did this come from? Actually, it's the case that the exponential functions show up so much in mathematical and scientific work that the hyperbolic functions were developed because they relate to expressions that popped up a lot. The hyperbolic cosine of x is defined to be e to the x plus e to the negative x over 2. And from these two, you can verify that the hyperbolic cosine squared of x plus the hyperbolic sine squared of x, nope, I don't mean plus, I mean minus. If you verify it, you'll see it is equal to 1. Well, that's very much in keeping with what we just wrote down as the equation of the unit hyperbola, right? X squared minus y squared is equal to 1. So it should make sense that the hyperbolic cosine squared minus the hyperbolic sine squared is equal to 1. Just like with the unit circle, we have a Pythagorean identity, right? X squared plus y squared equals 1 translates to the cosine squared of t plus the sine squared of t is equal to 1. We can define other hyperbolic functions, and they go the way you would expect if you think about it here. The hyperbolic tangent of x is defined to be the hyperbolic sine of x divided by the hyperbolic cosine of x. Likewise, the hyperbolic cotangent of x is the hyperbolic cosine of x divided by the hyperbolic sine of x. And we have reciprocal identities as well, with the hyperbolic cosecant of x and the hyperbolic secant of x playing the same role as they would with trigonometric functions. Using these definitions for the hyperbolic sine and the hyperbolic cosine, we can come up with their graphs. And that's what we have here. So in this graph on the left, what we have is y equals 1/2 e to the x. And on the in green, we have y equals negative 1/2 e to the negative x. And so if you add those two together, you get the expression that defines the hyperbolic sine of x. And using graphical addition, that is basically adding the y coordinates for the blue graph and the green graph, we get this red curve that gives us the hyperbolic sine of x, or y equals the hyperbolic sine of x. Likewise, here in the middle we have y equals 1/2 e to the negative x in green, that's an exponential decay. Y equals 1/2 e to the x in blue, exponential growth. If we add together the y coordinates for any particular x value, we end up with the red curve, which is the hyperbolic cosine of x. And finally, the ratio of hyperbolic sine to hyperbolic cosine will give us the hyperbolic tangent function, and we can see that there are horizontal asymptotes at y equals 1 and y equals negative 1. To conclude our introduction to hyperbolic functions, I'd like to show you two images. One of them is what's called a catenary. It's this shape that's made by basically a telephone wire that's between two posts. And I don't need you to pull a lot of details out of this, but the catenary has an equation that involves a hyperbolic cosine. So the shape of that sagging cable is actually a hyperbolic cosine. And the second image is the gateway arch. It's a structure in St. Louis, and it was designed using a hyperbolic cosine function. This is a picture out of our textbook. This is a homework problem out of our textbook that we're not going to analyze right now. But we can see that there is an equation for the St. Louis arch, and it's y equals 211.49 minus 20.96 hyperbolic cosine of 0.03291765x. Of course, I usually guess those numbers when people ask me to pick a number between 1 and 10. The point here is x and y are measured in meters, and x is between 91.2 and, well, negative 91.2 and 91.2. But the point, the shape of the arch is a curve, and it is a hyperbolic cosine.